Chapter 18, Part 3, we are going to continue working with sampling distributions, but this time we are going to look at sampling distributions for means or for averages. Now there's only one assumption here. The only assumption that we have to make is the independence assumption, which is that these sampled values must be independent of each other. This is usually pretty easy to determine, so just make sure you're thinking about whether each sample or each person that you ask, whoever you're getting that data from, is independent of the other. Now I apologize, your numbering was a little messed up on your paper, but there are 3 conditions for using the normal model, and again we have to check these conditions every single time. What's really nice is that the first 2 conditions are the same as we saw for proportions, but that third condition is a little bit different. So our first condition is our random condition. Just like we saw with proportions, we want to make sure that if the data comes from an experiment, the subjects have been randomly assigned treatments. And if the data comes from a survey, we want to make sure that our sample was attained in a non-biased manner. Again, sometimes it might not say random. That's okay if your sample represents your population. So if it doesn't say random, but you believe that your sample represents the population, then you're still okay here. Condition 2 is again our 10% condition. This says that the sample size of n must be no larger than 10% of the population. Okay, the third condition is called the normal condition, and this one is different than what we saw in proportions. In this third condition, what we need to do is make sure that our population is normal. Now there's 2 ways that we can check this. One, they might literally just tell you, hey, your data is normal, it's normally distributed. If they tell you that, you're good to go, you've already met this condition. Now, most of the time they will not tell you that, so what we will do is make sure that we have a large enough sample. So we need to make sure that the sample size is large enough. We're asking enough people so that it should follow a normal model. Now, this isn't always true, but typically what we say is that we want our sample size, our n value, to be greater than 30. If it's greater than 30, then it will meet this normal condition. Okay, now that we're working with means, our formulas for mean and standard deviation are a little bit different. In these problems, they're not going to give you proportions, so there's not going to be any P's and Q's. Instead, there's going to be means and standard deviations. So when I'm finding the mean, I'm going to find the expected value of my sample mean, which is my x bar. So this is what I expect to happen in my sample, what I expect my average to be. Now I expect my average to match what's happening in the population, so we are going to use our Greek letter mu. Okay, for standard deviation, we're finding the standard deviation of our sample mean, so again, what we expect to happen in our sample. And when we go to find this, what we're going to do is take the standard deviation from our population, which is our sigma. This is the standard deviation from the population. So I'm going to call this population standard deviation. And what we're doing is adjusting the standard deviation to our sample size. We do so by dividing that standard deviation by the square root of our sample. So the square root of n. Okay, again, by checking that third condition, no matter what the population random sample comes from, the shape of the sampling distribution is approximately normal as long as that sample size is large enough. So that's kind of the big difference here, is making sure that we have the normal model, either the population is normal or making sure we're asking at least 30 people. Let's go ahead and look at a few examples on the next page. Okay, example 1 says, a college physical education department asked a random sample of 200 female students to self-report their heights and weights, but the percentage of students with body mass indexes over 25 seemed suspiciously low. One possible explanation may be that the respondents reported lower than accurate weights. The CDC reports that the mean weight of 18-year-old women is 143.74 pounds with a standard deviation of 51.54 pounds. But these 200 randomly selected women reported a mean weight of only 140. So what we're expecting it to be is 143. The 200 women we asked only gave an average weight of 140. Our job is to answer the question, does the mean weight in the sample seem exceptionally low, or might this just be a random sample due to sampling variation? Right, now one thing I do want to point out is that the information they're giving me is a little bit different. This time they are giving me means and standard deviations. Because they're giving me means and standard deviations, there's no proportions or no percentages, this is a great example of sampling means. Now, just like we did with proportions, I like to start with writing out my variables. There should be two things they tell you from the population. That's your population mean or average, so mu, and they should also give us the population standard deviation, or sigma. In this problem, they said that the CDC reports the mean weight to be 143.74, so that's what's happening with the population of all 18-year-old women. The standard deviation was 51.54. Now this college collected data, so we should have a sample size, an N value. It looks like they asked 200 people. And from those 200 people, we should be able to find another average. This is the average from our sample, so I'm using X bar. That sample mean was 140. Okay, once we have our variables, we can go ahead and check our conditions, make sure that it's okay to use a normal model. So my first condition is that the sample must be randomly selected. It literally tells me in my problem randomly selected, so that random condition is definitely met. The second condition is again my 10% condition, so I need to make sure that my sample is less than 10% of the population. I definitely think that 200 18-year-old women is less than 10% of all 18-year-old women. Okay, now when we were working with proportions, this third condition was to take our P and multiply by N. I don't have P here, so this is where that third condition has to change. This is our normal condition. Now it will either tell us that the population is normal, which it didn't say anything about things being normal or normally distributed. So instead I'm going to look at my N. N is 200, which is definitely over 30. So I'm going to say this is a large enough sample. And I like to just clarify on here that N is definitely greater than 30. Once I have my conditions, I can go ahead and find my mean and standard deviation to start building my normal model. So I'm going to start with finding the mean, or what I expect to happen. Now I expect that mean to match the population, so my mean for this sample is 143.74. Standard deviation, just like with proportions, we're going to have to do a little bit of work here. What I'm going to do is take my standard deviation from the population and divide by the square root of my sample, which is 200. Oh my goodness, I'm way up there. Alright, 51.54 divided by the square root of 200 gives me 3.6444. Again, I'm always going to go to 4 digits after the decimal. I have my mean and standard deviation, so I have enough to build a normal model. My mean is that 143.74. Standard deviation we just found to be the 3.6444. Okay, now the question's asking me, does the mean weight in this sample, so that's the 140, does that seem exceptionally low? So I'm going to drop down 140, it's going to be somewhere over here. They're not asking me for a probability, so I'm not going to have any shading here. All I want to do is just change that 140 from my sample into a z-score to see how unusual it is. So I'm going to take 140, subtract 143.74, divide by standard deviation. So I have a z-score of negative 1.03. Okay, that means that this sample, although it was below average, it was only about 1 standard deviation below average. So do you think this is exceptionally low? I would say no. It's not very unusual or very low, because it's only 1.03 standard deviations below average. If it were, say, 3 standard deviations below or more, then I would say that it's very unusual. All right, let's take a look at another example here. Okay, example 2 says the Center for Disease Control and Prevention reports that the mean weight of adult men in the U.S. is 190 pounds with a standard deviation of 59 pounds. An elevator in an office building has a weight limit of 10 persons or 2,500 pounds. What is the probability that if 10 men get on the elevator, they will overload its weight limit? Okay, so this one's going to be very similar. I am now finding an actual probability. So once I have my normal model and my z-score, I'll use normal CDF to find that probability. So I'm going to start with finding those variables again. Mu should be the average for all adult men, which they tell me is 190. The standard deviation, 59 pounds. Okay, now my n value in this case is the 10 men that are getting on the elevator. And I think this one's kind of tricky, so they're not really telling you the average. We have to find that average ourselves. So the weight limit on this elevator is the 2,500 pounds. We're trying to find that if 10 men get on, they're going to overload its weight limit. So to find that average, what we would do is take the 2,500 pounds, that's my limit, and divide it by the 10 men getting on the elevator. Okay, that should give me 250. So these 10 men would have to have an average weight of 250 pounds in order to overload the elevator. Okay, we'll go ahead and find our conditions again. First one is that it must be random. I don't think that the 10 men getting on the elevator are necessarily random, but I do think that just 10 men should represent all men. So I'm going to say 10 men should represent all men. There's nothing indicating to me that these 10 men are exceptionally heavy or exceptionally, unheavy, but I think that they should be a good representation of all general men. Next, I'm checking that I have less than 10% of my population. I definitely think that 10 men is less than 10% of all men. And my last one, I need to make sure that I have a normal model. Going through and reading again, I don't see anything saying that this is normal, and my sample size is quite small. I only have 10 men. So this does happen sometimes. In order for me to proceed, what I would have to say is that the weight of US men would need to be normal. So I'm going to say weight now, I know it's not telling us that it is normal. Typically, weights and heights are normally distributed. So if you just wrote this right here, that would be good enough to proceed. I will go ahead and find our mean and standard deviation. The mean for my sample, I'm expecting it to be the mean from the population, so just my 190. And to find my standard deviation, I'm going to take the standard deviation from the population, so the 59, and divide by the square root of my sample. So I'm dividing by square root of 10. We get 18.6574. From here, I can draw my normal model because I have my mean and standard deviation. I am looking for the probability that these 10 men will overload its limit. So we found an average of 250 pounds for those 10 men. And if they're overloading the weight limit, that means that it would have to be greater than 250. I'll go ahead and change 250 into a z-score. So 3.22, which is pretty high. And then we can use our normal CDF to find that actual probability. My lower bound is that z-score we just found. Upper bound is just a very large number. Mean and standard deviation stay the same. And we get 6.4 with an e, so times 10 to the negative 4. So very, very, very small probability here that 10 random men will overload the elevator. All right, taking a look at example 3, this says speeds of cars on a highway have a mean of 52 miles per hour and a standard deviation of 6 miles per hour. They are likely to be skewed to the right, so a very few fast drivers. Describe what we might see in a random sample of 50 cars. So again, I'm going to start with listing my variables. The mean that they're telling me is 52. My standard deviation, 6. I am asking or surveying 50 cars, and the average for that sample, they don't give us, we don't know. That's what we're trying to find out, is what do we expect to see. Again, starting with my conditions. Okay, first one is random. Do we think that these 50 cars are random? Well, in this case, they told me we are going to be looking at random samples. %% condition, I definitely think that 50 cars is less than 10% of all cars on the highway. And the third one is my normal condition. This is another weird one. They are telling you that the population is likely to be skewed to the right, so that's the population here. But because I'm asking enough people, my sample size is 50, which is definitely greater than 30. I'm okay to assume that this will be normal. So I'm going to say large enough sample n is greater than 30. So we are good to use that normal model. Again, we'll find our mean and our standard deviation. The mean for my sample is the mean from my population, so just 52. My standard deviation, I'm taking the population standard deviation, so 6, and dividing by the square root of n. So 0.8485. Good to build my normal model. Okay, now in this example, they're asking us to describe what we might see. So this is kind of like we saw with proportions, where we know that most of our samples should fall within 3 standard deviations on this model. So I'm going to find what the average speed will be for 3 standard deviations above and for 3 standard deviations below. So to do that, I'm going to take my mean, so I'm going to do 52. I'll start with this left-hand side, so I'm going to subtract 3 times my mean. And I'll do the same thing, but adding on the other side. Okay, now that I have my 3 standard deviations above and below, I know that most of my samples should have speeds between here. So I'm going to say we can expect, you could say most samples, you could say most is really meaning the 99.7%. So we can expect most samples, or we can expect 99.7% of samples to have an average speed between 49.4545 miles per hour and 54.5455 miles per hour. This is what we are expecting to see in most of our samples. Right, I want to go through one more example with you. The process I think we should have down at this point, but the information that they give you in example 4 looks slightly different. So in example 4, they said the College Board reported the score distribution shown in the table for all students who took the 2006 AP Stats exam. So here are the possible AP scores, and then they gave us the percent of students that got each of those scores. So 12.6% of kids got a 5. Right, now in our last several examples, they just gave us the mean and the standard deviation. In this case, they're giving us the data. So we are going to use our calculator to find the mean and standard deviation of these scores. So in our calculator, I want us to type this data in. I'm going to put the actual score into L1 and the percent into L2. So I'm at stat edit. Oops. Okay, because these are percentages, I'm going to change them into decimals. So this would become 0.126. So just moving that decimal to the left. Okay, from here we're going to stat calc, And we are technically still just looking at one variable. The variable was that score on the AP exam. So I'm going to this first one variable stats. And the only thing that we need to look out for here is this frequency list. Frequency means how often something is occurring, which is a probability. So I need to put L2 here for that frequency list. I already have it up there, but if you didn't, you would hit second and then 2 to get that L2. Now when we've calculated, it gives us the mean and the standard deviation. Now your calculator writes it as x bar, but technically this is from the population, so this is mu. So we're going to write that as 2.859, and my standard deviation is the 1.3241. Once we have that mean and standard deviation, the rest of the problem here is going to stay the same. So part B says, if we select a random sample of 40 AP statistics students, would you expect their scores to follow a normal model? Explain. So because that random sample of 40 is greater than 30, I would say yes. I'd expect the sample to be normal because the sample is greater than 30. Okay, part C says consider the mean scores of random samples of 40 AP statistics students. Describe the sampling model for these means. So they want the shape, center, and spread. Now shape we already have, we know it's going to be normal. So the only two things we need to find are the mean and the standard deviation. So the mean for that sample would just be the mean from my population, so the 2.859. Standard deviation, we will again take the standard deviation from the population, divide by the square root of my sample. I think the best way to answer this question would be to show your work, but then to also draw it on your normal model, showing that you know where the mean and standard deviation are located in relationship to that shape. Hopefully you notice that there are quite a few similarities between proportions and means. My big recommendation is when you are given a problem, start with deciding whether you think you are given a proportion or a percentage, or whether you're given a mean. That should help you determine which formulas to use and which conditions to check.